Thank you. And hello to everybody. In case you don't know me already, my name's Susie Ferguson and I'm based at Wood, which was back in the day I was at Foster Wheeler, which then became AMEC Foster Wheeler and is now part of the Wood Group. Or rather, we are now called Wood because we joined with the Wood Group. Let me just get my slides ready. So whilst we have done a lot of things like technology evaluation through to cluster development and feed projects, it's nice to have this opportunity to talk about what we think would be useful in terms of research needs. Can everyone see the slides okay?
Yes.
Yep.
So I only have 3 slides of ideas.
Sorry, yeah, Ali.
The first one, I've just got this one slide on things that we would like to see that could be very useful for CO2 capture processes as a potential research topic. And that's because we've had a lot of challenges that we've seen in this area with trying to support our clients to make sure that their projects are the best possible projects they can be in terms of environmental benefit. Because let's face it, all of our CCS projects have the ultimate aim of being very positive for the environment and tackling climate change. And it's important to make sure that we're also doing minimum environmental impact at the same time. So when we look at individual issues, such as minimizing solvent degradation and therefore minimizing NOx to minimize solvent degradation, what we've come across when we've looked at the total holistic plant design, which is something that we tend to do, putting together the pieces of the puzzle to come up with the overall project. Often there's a lot of interplay between potential mitigations, which can lead to complications. So something that would be really useful from my point of view would be some sort of quantitative guidance on things that could help us to make decisions about what's the best environmental direction to go in. And a lot of this has been discussed in the back group already. So I'm sure John Gibbons will have seen a lot of this already. So this is really looking at things like, is the overall project benefiting from things like adding an SCR, because that can lead to having more ammonia coming out of the flue gas, which you then need to try and abate by adding an acid wash, which then gives you more environmental issues in terms of water treatment. And one of the projects that we were looking at would have to send their wastewater from the acid wash to off-site treatment. So really, I just wanted to see what people thought about this idea of trying to create a tool that can add some quantitative guidance so that people can understand, is it a good idea to at what level of NOx is it more beneficial to put up with the amine degradation and have the NOx emission in terms of total environmental benefit compared to adding all of these mitigation measures, which have their own unintended consequences as well. So this is my suggestion from the area of CO2 capture, specifically for post-combustion applications. Then in terms of hydrogen, I can't imagine anyone will be too surprised to see this suggestion. So Wood wears 2 different hats when it comes to blue hydrogen generation. And that is our group in Milan are specialists in terms of being a licensor for steam methane reforming technology. But in the UK, in our consultancy office, we're very much technology neutral, and we very frequently do licensor selection for things like hydrogen units in particular for a refinery, where we'll get multiple bidders in, and it won't always be our technology that gets put forward. It will be the technology that's right for the project. So something that I would like to see is that very often, because of the nature of how we're trying to predict the future and where the future is going to go, it's completely understandable that where information is available on a technology like the ATR with gas heated reformer, and that particular information that's in the public domain has a better performance to, say, the SMR that is in the Bayes benchmarks, it's completely understandable that all of the models that are subsequently developed from this, like the energy systems models, would therefore always choose an ATR with the gas heated reformer. But what we would like to see is, or what that we understand, is that there are 3 different technologies that are all very level on competition point of view, And it's very difficult to understand whether or not there's a genuine difference in terms of the technology's ability to compete or not. The chemistry, when we have modeled it as an independent consultant's point of view, is actually very similar certainly between the ATR and the SMR routes, with some of them more beneficial for different applications. So something that we would like to see would be to have a completely independent body take a look at the underlying chemistry and processes involved with these 3 different routes to producing blue hydrogen, and to make sure that there's something in the public domain that says, if there are differences, point out what the pros and cons of each of the individual technologies are. And if there is a clear winner, to show an unbiased view that everyone can then reference to say which one of those is leading for whichever reason, and which have setbacks or different applications when they're more appropriate. And this kind of study would also be useful to be expanded into the future to perhaps cover an idea of high-level costs for things like biomass and waste gasification and biohydrogen routes for carbon negative technologies, and to also potentially consider disruptive technologies that completely change the route of how you can make blue hydrogen, like cracking of methane directly to carbon and hydrogen, or incorporating sorbent enhanced water gas shift, which could also be a really impressive technology once it's achieved a suitable level of demonstration that we can work out how much that's going to benefit the projects. And then my last slide is just two other ideas that I wanted to throw out there. And it may be that this has already been covered, and I personally don't spend a lot of time reviewing what's available and what has already. So apologies if you know that there's studies that have already been put out into the public domain and I just haven't seen them yet. I think it would be really useful to see a review of feedstocks that are available in the UK that can be used to make negative emissions hydrogen. And that's either sort of light liquid feedstocks, for example, if there are any bioethanol type glycerol sort of waste streams. So glycerol is a byproduct of making biodiesel from vegetable oils. And it's particularly suitable for reformation, which if you put CO2 capture on that reforming plant, you would have carbon negative process depending on all of the other life cycle emissions through the process. And the same for gasification. How much biomass and waste is realistically available when we take into account that we hope to have a more circular economy going forward, and therefore less use of plastics going to landfill or incinerators that would then provide feedstocks for gasification. So how much hydrogen could we make by these different routes, I think would be really interesting. Then on a much more technical point, there are challenges when you take an existing fired heater and you want to increase the quantity of hydrogen in its fuel gas or change its fuel gas in some substantial way. So we've looked at some really interesting projects where we would replace refinery fuel gas systems with hydrogen, or increase them to say 50% hydrogen. And the same for a steel plant, where we'd look at removing this carbon monoxide, which is a major component in their combined fuel systems on a steel plant, to decarbonize the fuel system, use that CO somewhere else in a unit with post-combustion. But what would the impact be on the physical pieces of equipment in terms of the amount of radiation that is hitting the physical equipment? What's the impact on things like the refractories and the radiation within the firebox? Because when you have an invisible flame, it's going to be very different from when you have a highly luminous flame. So anything that can look into that can be useful for people who say have a refinery fired heater, they want to know if they can swap it out to hydrogen as a test, and they're looking for something in the public domain they can use as a basis. And that was everything I had. Thank you very much.
Thank you, Susie. That's great. I am muted. Am I?
No, I can hear you.
Oh, good. It was a depressing message one sees. Oh, that's great. I'm really, that's some really nice thoughts, Susie. I love them, even if I don't understand them all. I'm sure a number of our listeners will. Now, shall we move over to Petrofac, or do Do we want to ask questions now, or are we going to leave that till after?
To have the discussion after and come back, unless there's any like very immediate questions.
Okay.
But I think a discussion kind of after all the presentations would be good to kind of try and draw some of these ideas together, if that's okay.
And you're reassuring people that they can get the slides as such, can they?
Yes, so we've got permission of all of our speakers to share slides following the call as well.
So any quick questions for Susie before we move on? Excellent. I think there's good food for thought there, though. Now, Shet from Petrofac, I don't know you, sorry, so I have got no clue as to what you're on about. So I look forward to seeing what you've got to say. Thank you.
Right. Well, thanks for that introduction. I am Chet Buliok. I know quite a number of people in this call, and I have worked with a number of people in the past when in my days when I was an academic from 5 years ago, actually 6 years. That time flies. So so let me just share my thoughts. Susie, your presentation is a tough act to follow, I would say. The thoughts I have really are based on projects that we are working on currently. Think the kind of challenges we are facing, and they are mainly kind of systems challenges or cross-cutting challenges rather than technology focused. So, let me start with this nice differentiation of blue-green hydrogen. Our focus really, this is UKCCSRC, so it will be blue hydrogen. However, there are commonalities that require some bit of focus in terms of research and taking things forward and ensuring that the projects are successful. Over the past 6 months, I've been working on this Arrowsmith Green Hydrogen project. I've been the process lead for it, among the other things I do at Petrofac. It's a project I'm delivering in Australia. It's going to be based in Perth. We are rounding up with the feed now. And it's going to be a 5 tons per day project using solar, wind, and grid connection to generate hydrogen with electrolysis. So it's not the kind of thing that we are focused, UKCCRC should focus on, but the areas of interest really are, for me, would be the storage and what we are doing there because of the challenges we've been facing. So my thoughts on that area is that now that we're generating lots of hydrogen, or we'll soon start generating lots of hydrogen, large-scale storage of hydrogen is a really challenging thing. Hydrogen, very tiny molecule, occupies lots of volume at low pressure, so you need to store. This 750 bar gauge is a target because that's the pressure at which you fuel your. So when you fuel your hydrogen vehicles, that's the pressure at which hydrogen is stored. So that's a kind of let's say minimum that the number of projects are looking at because of the application. So storing that large inventory is storing that hydrogen at that pressure and large inventory is challenging. There are mechanical limitations on vessel diameter and all the other things around that. We've been doing electrolysis at small scale and storing hydrogen at small scale. So there have been composite tanks or composite vessels developed for those. Those are quite expensive. We need to move from that quite quickly and look at other storage mechanisms. So also then there is if you want to store hydrogen and liquid, you're basically talking about LNG, even lower than LNG temperature. This is minus 253, 54 degrees Celsius that you want to store the hydrogen if you're going to store around the atmospheric pressure. So those are things that require a lot of energy. So what should be the target in research that we're looking for hydrogen for hydrogen? So we want to get the secure electricity storage, and we want to look at also the gaseous and liquid offtake, because at the moment we are talking about using hydrogen, but in the UK in particular, the usage routes or the offtake routes are not that available. Grid blending has been talked about for a while, and I think the standard is still 0.1% of hydrogen is allowed in the grid. I think someone mentioned that Europe does up to 20%. That's something that really opened things quite quickly. But really, we should think about how we can be using the hydrogen very quickly so that we get the industry going quite forward and moving forward. So the few ideas I have around this area that academics can get their thing into is looking at really flexible, viable storage mechanisms other than the salt carvings that are not widely available and distributed, right? So yes, you have the composite vessels and all that, but what other large scale storage? What other energy efficient or shall I say viable or economic large scale storage of hydrogen should we be really looking to develop for that? What ideas do we have around that area? How can we reduce the energy? This is simple, will I say standard optimization kind of approaches to reduce energy consumption in storage. So whether you want to compress it to crazy pressures like I just pointed out, or even liquefy it. So how can you reduce the energy usage in those kind of things? The final thing I want to point out is, well, as we are starting up, how do we optimize the hydrogen? When I say supply chain, I'm talking about the demand and supply of hydrogen. So where do you locate your blue hydrogen plant, and what are the off-takers or what are the industry around it that will be able to use the hydrogen that would make sense, make it economic to put that hydrogen, that blue hydrogen facility there. So those are kind of ideas that I have, and we can I think that would be a good start for hydrogen. Now moving on to CCS. I see Ian is here. I'm going to talk about Acorn, but when Pale Blue Dot is here, so apologies, Ian. This is something you already know quite well. In fact, more than me. So I'll just cover it quite quickly of what Petrofac is doing in Acorn. So for CCUS, I just want to point out that it's a large value chain, right? I think it should be really focused around the technology for CO2 capture, but then the value chain is vast, right? You have the industries or whatever facility you're capturing the CO2 from. You have the tie-ins, you have the utilities, compression conditioning, pipeline, subsea wells, monitoring, direct air capture, bunkering, liquid transportation. So you can take your pick, right? And this is what we see really in Acorn, which is a project that Petrofac is supporting as the project management office on Acorn. So we're supporting Pale Blue Dot, providing our technical expertise to push the project forward. So which looks very good. At the moment, the first phase, which is the 350 tons 350,000 tons per annum facility that should be moving forward to and getting developed. And there is future expansion as well to consider for the Acorn. So there's a hydrogen hub on that development now. All of this is publicly available information, so I'm not sharing anything new here, but this is things that everyone knows. So I'll just keep this slide quite quickly. So what am I looking at systematically around Acorn? And I'm sure I'm not the only person that will talk about this. When I can see, I know someone will talk about measurements very soon. So metering, really cost-effective metering and fugitive emissions is something I want to focus on. Again, very systems approach. The thing about CO2 is that it's essentially a waste stream, so we don't really require that much, let's say, accuracy in terms of measurements and all the whole custody transfer and and those kind of things that go around metering. Yeah, and really the considerations really for metering and for CO2 purity or quality should really be be materials. We should ensure that the CO2 transport is not doesn't have free moisture to be corrosive, to impact the integrity of the transport infrastructure and all the other good stuff around that. So we should let's keep that in mind, right? So rather than really trying to make and get stringent quality required for CO2, yes, it's a waste stream. We're trying to get rid of it. So how do we do that effectively? Another thing that comes to mind is I can say typo here. This should be 2021. So in my previous life, as part of another entity, I did a lot of work in terms of the emissions from CO2 capture plants, fugitive emissions in particular. And so one way in which limits are set is that dispersion analysis is done at some point, but it's becoming clear to me that there is no that appreciation of the impact of fugitive emissions in terms of limits, and that's something that will become clearer as we do a lot of these facilities. So it's good to have a limit on one facility in terms of dispersion, right, around the surrounding areas. But when you start building, and this is something that me and John were discussing a few months back, when you start building a lot of these post-combustion capture facilities, and at the start is going to be using amines most likely. What are the limits? What's the impact on all of those limits that you've set on those facilities? They compound or they add up. So that area needs really to be coming up, or at least coming up before more and more. So what are the targets I see that in terms of research? So standardized metering approach that can be applied across the clusters that are being developed. That would be very nice, and clearly understand the limits on amines or amine-like compounds that come out from the top of the absorber. So what are the ideas I'm looking at? Yeah, so the metering is something that we've been doing. Gas, natural gas, LNG, and all that. What kind of cost-effective approach can we take? Yes, gas, LNG, those are valuable stuff. How else can we approach metering that will make it cost-effective and not stringent in terms of and the next point, what kind of quality specification for CO2 should we go for? I remember last week I sat on the call with James Watt, and he talked about a standard that has been published for CO2 quality for pipeline transport. I think that's a good start. It's not as stringent, but we really should be looking at, we don't want to make it 99.99% CO2, right? We should have some relaxed non-condensable gases. Maybe we can relax it for oxygen and water, but at least for nitrogen and all, which we should be able to manage at least within those relaxed standards, so that will not be too stringent, and give the capture facilities some flexibility in what they're able to provide. Then the final thing is that what kind of devices or that are available in terms of limiting fugitive emissions coming out of the absorber. Yes, we do our water wash, and Susie mentioned the acid wash. There are other devices that at least that I've designed in the past and that people have looked at, particularly in targeting aerosols coming out at the top of the absorber. So what's available out there? What can we really look at implementing that will limit those fugitive emissions? Because it adds up. Whatever limits we put, it adds up, and particularly if the industry grows quite quickly. That's what I have for you. Again, systems approach, and it'd be nice to see what the discussions come up with.
Okay, well, thanks, Chet. That's I like your couple of your points that will, I think, good to follow up on. But perhaps any other immediate questions from anyone before we move on, because we're running on time. So hopefully everyone happy for the moment. Oh, okay, thanks. We'll thanks, Jet. And we'll move on to Keith Birch at Suez. And we can see 7 slides here. So let's go for it.
Hi there. Can you see my slides okay?
Yep, I can see the screen with the whole of the presentation on the left-hand side.
Okay, let's just try it. For some reason, I can't see the controls and the screen at the same time. So you can still see that okay?
That's perfect.
Right, I will blow through these slides very quickly and come to the last one, which is the main talking point. My name is Keith Birch and I work for Suez Group, and we are one of Europe's largest owners and operators of waste recycling collection facilities, also water treatment, sewage treatment, and specialty chemical supply and technology business. And what we are here to talk about today is really energy from waste, because that's our largest area of CO2 output, and it's a key area we think in carbon capture storage projects going forwards, and also potentially to some extent hydrogen projects as well. So there are 3 main conversion technologies involved in energy from waste, and they're combustion, gasification, and digestion. And we use all 3, and we own and operate all 3 types of plants. And we make the selection as to what type of plant we're going to use, and based on, broadly speaking, what's the most energy efficient solution. And in the case of the project we're going to talk about today, and the majority of the UK, that's energy from waste through direct combustion. So in terms of the process takes pre-sorted waste. So we collect, and I've used the example of the Teesside project. So we collect all of the waste from Northumberland, from the local authority, from houses, etc., businesses. And we sort that waste and we remove everything which can be currently recycled, and we are left with a residual material which is burned. And you can see a layout of the plant here. So we mix the fuel, we put it into a combustion system, we generate steam, and we use that to spin a turbine. We then have a gas emissions reduction and cleanup system which sits on the back end. This is what the system actually looks like. So this is the grate itself. It's a moving grate, and the refuse is placed on that and incinerates as the grate moves. The particular project that we're talking about today is the Net Zero Teesside, which is now combined with the Humberside hub, as I guess many of those on the call will be familiar with. So the plan here is to build a ring main system for the collection of CO2 from industrial users. That will be combined with the output from a dispatchable power plant, which will be built by owned and operated by BP on behalf of the Net Zero Teesside hub, and that will then send dense phase CO2 out into the North Sea for storage in the Endurance Aquifer. We have 2 facilities on the complex, each of which has multiple trains. The site we're looking at for our initial development is the one that's identified here as Haverton Hill, and we're proposing to put 162,000 tonne a day capture facility onto that plant, and that represents 2 incineration lines at that facility. So in terms of our previous expertise in this area, we have a division which we call Suez Oil and Gas Division, and they have been involved in both carbon capture for standard conventional onshore and offshore oil and gas projects in the past, and then also quite a lot of work, particularly in Australia a few years ago, around building skids for carbon capture storage, with the largest plant being the 18,000 tonne a day pilot at the Hazelwood coal-fired power plant down in Australia. And we have experience of, within those pilot plants, a wide variety of different solvents. So moving to the top left, this is the an overview, aerial view of the Teesside facility, the Haverton Hill facility, with a graphic there. You can see next to one of the existing plants, there's actually 2 plants on the same location, and you can see that we've superimposed our proposed 162,000 tonne a day unit there. And the last slide is kind of where we're up to, in that we have pre-feed work in progress, and we have a number of designs on the table, or a number of variations of the design on the table. And it's interesting that the previous 2 speakers highlighted many of the issues which we are now facing. So first off is what amine do we select, particularly based on the impact that amine selection has on the energy balance from the site, and the impact on the existing output of the plant. What are the utility requirements? And then the biggie really, which is what is the impact on effluent and emissions of both the amine selection and then the technology that we use to mitigate any emissions. So I think both of the previous speakers identified nitrous amines, particulates, aerosols, and there's a real lack of information around many of those things. There's also a lack of information about metering and monitoring, and then also around decisions like, do we bring the output from the regenerator column, do we vent that directly to atmosphere, or do we bring it back into one of the existing stacks where it goes through the existing SEMS monitoring system and through the existing dispersion model? There's also then what impact does it have on the back pressure, the flow of air, etc., through the existing facility. And these are all issues which we are working with real time now, with particularly the funding window for UK government grants being kind of this year, and needing to be in a position by the end of the year that we have a reasonably accurate assessment of what the cost of this plant is going to be, what the business model is going to be, and what the return will be, so that we can then start presenting that both to our own board and to third-party financing from outside. So those were our slides and our thoughts on areas for investigation.
Right. Yeah, it's a real urgent problem there, isn't it? That you've got, and but I think it does point the way to where R&D will have good value in the future. Thanks, Keith. Any immediate questions from folk? Good. Well, we'll save it up for the discussion a bit more. And so we've got Emma from NPL on, and I think we're doing well. Thank you very much. Thanks, Emma.
Thanks. Can you see my screen okay, just to check before I kick off?
Yeah, looks good. Yep, you're full screen now.
Perfect, great. Okay, thank you for that. And thanks to the other speakers for a great lineup of presentations, and to Karis for inviting me to speak. So for those who were at yesterday's session on transport and storage, my colleague Sam Bartlett presented on behalf of NPL. So I'll just very quickly run through some intro slides just for a bit of context, and then go into specific research needs and more specifically measurement needs relating to carbon capture, and also touch a bit on hydrogen as well. So my name's Emma Richardson. I'm part of the Energy and Environment Strategy team at the National Physical Laboratory. So this is the image here on the screen is the site in Southwest London in Teddington, our main laboratory site, but we also have a number of pilot sites around the country. We have NPL Scotland at the Uni of Strathclyde, and a number throughout the rest of England that also undertake measurement science on behalf of NPL. Okay, so very quickly, I'll just run through a bit of a background for those who don't know who NPL are. So we're actually a government-owned laboratory. So we are part funded and wholly owned by BEIS. They provide funding to NPL on an annual basis to maintain our role as the UK's National Metrology Institute, and metrology being the science of measurement. So we do receive part of our funding from BEIS, but we also, to maintain that baseline capability, but we also undertake commercial projects like a normal organisation to make sure that that capability is then transferred across to industry and other stakeholders. So really our role is to provide decision-making confidence and in support of trade, innovation and broader societal ambitions. And the way that we do that is through 4 primary sectors at MPL, which are advanced manufacturing, digital, health and life sciences, and the sector that I work in, which is the energy and environment sector, which is most applicable to today. We have around over 1,000 scientists working at MPL across our many sites. And as I've mentioned, it's predominantly to provide measurement capability that is traceable to the SI units, which is what the purpose of a National Metrology Institute is. And most countries around the world have their own National Metrology Institute, and MPL is the UK's. And just a very quick point to cover off is in terms of how we approach measurement science at MPL. Really, our remit and our interest is whether the answer is right rather than what the answer is. So similar to what Susie touched on earlier, we were pretty unbiased when it comes to technologies and approaches to reaching the target of net zero and tackling climate change. We more care about what the answer, whether the answer is right, rather than make the decisions on which technology is the best approach. That's left over to the policymakers. So very briefly, as I mentioned, I'm part of the Energy and Environment Strategy team, and what that entails is looking at the entire worldview, as we call it, of the energy and environment sectors, and where metrology or measurement could play a significant role. So this is a very condensed version of our strategy document. My role at MPL is to cover the entire breadth of these themes. So CCUS and hydrogen are just 2 themes that I cover at MPL. So we do have a number of science areas and experts who are specific experts on certain themes. So for CCUS, we have expertise across emissions, gas metrology, data science, temperature and humidity, to name a few. And really my role is to make sure that we're looking at the broader picture and how MPL can be embedded in those sectors to add most value. So you can see CCUS is there on the screen as part of our strategy. Hydrogen falls within our energy vector theme. But you can see we cover really the entire breadth of activity that's related to energy and environment in the UK. So very quickly, a bit of background on what I do and how we came to the research needs and the measurement needs that I'll be talking about in the next few slides. So really my role at MPL is to conduct these sector reports, to do a deep dive of understanding on how measurement science can add value to certain sectors or certain future themes. So really the process is to conduct a literature review, that's standard. Stakeholder engagement in an event is really the bit that's probably of most interest to you all, and hopefully some of you would have joined our webinar series that we held in October last year, which was really to get industry input and stakeholder input into what the most high priority measurement needs were from our perspective, and understand whether there were any that we were missing, so that MPL could get a whole view of what the needs were across the entire CCUS supply chain. And we broke that down into capture, transport, storage and usage. More specifically, that was then put into a CCUS report, which we launched in February of this year, which is free to download and available from our website. I'll provide a link at the end, and the slides will be shared, I believe. And then on that, we review this and update this on a regular basis to make sure that we're either tracking our progress against meeting those measurement needs and challenges, or identifying where projects have been developed or exist that are looking to support meeting those needs. So as I mentioned, we held the workshop last year. We had over 100 attendees from various different companies across not only the UK but internationally, working in the CCUS space. And really the purpose of these, as I mentioned, was to capture and validate what the high priority measurement needs were relating to CCUS. So you can see we did this through, usually we would host a workshop in person at MPL in Teddington. Obviously you couldn't do that this year, so we had held some online webinars, and we asked attendees to fill in an online form, as you can see on the right, to rank from high, medium, low, or not relevant, whether a certain research need or a measurement need related to, in this instance, capture, was applicable to their organisation or not, which allowed us to sort of filter out, well, not filter out, but prioritise more easily where we best put our efforts first, as obviously there's numerous things that could be done in terms of measurement needs, and we've got to apply a bit of filtering to that and prioritization to that. So this infographic that you can hopefully see on the screen was a summary of those high priority measurement needs that came out of that process. And we did this in a visual. We usually produce these infographics as a bit of more of a visual tool to support our report, and it's a bit more easily understood for people who probably perhaps don't work in the CCUS industry, for example, policymakers maybe who want to have an understanding of where measurement might play a role across the CCUS supply chain. So this is really just to show the processes and pick out some of the key challenges that we found through that report process. But in more detail, and probably of interest to people today, was the industry validated needs that we came up with, which we summarized through this table that you can see on the screen, and we broke those down in capture, transport, usage and storage. For the purpose of today, I'll focus on capture, obviously, and these were prioritized as follows. So the highest priorities as validated through MPL and also through our stakeholders was measuring and comparing the efficiency of different capture techniques and configurations to provide confidence in investments into technologies in support of CCUS business cases. And this includes a full lifecycle analysis and direct measurements of those capture techniques. The second being undertaking validation of analytical tools that would be used to perform online monitoring of impurities, which could indicate degradation of certain capture solvents or give a general indication of capture performance. The third, understanding impurities in captured CO2 to identify whether a purification step is required to meet any technical specifications, including any cross reactions between impurities from differing capture processes. And finally, reducing measurement uncertainties for CO2 emissions trading to ensure that we're compliant with both UK and international regulations in that space. So as I mentioned, the report was published in February. It's free and available to download. Happy to share it with people in this forum if people would like access to it. The link's there, and you can see some of the people that contributed to that prioritization are shown along the bottom of the screen. Very briefly, I know that we're also talking about hydrogen in this space. We actually conducted the same process I just described for CCS for hydrogen back in 2016. The exact same process was undertaken, a workshop stakeholder validation, and we also produced a report and an infographic that you can see on the screen that's also free and ready to be read for those who would like access to it. And in a similar sense, we set this out across the entire potential supply chain and use chain of hydrogen as well, in terms of production, distribution, storage, and then the variety of different end uses that hydrogen could have in terms of transport and combustion for heat. So the main top priority challenges that we found, or research needs, measurement needs that we found from that process, included materials development for fuel cells and electrolyzers, which is since 2016 an area of real focus to MPL, and we've been developing a lot of capability and working on a lot of projects in that space, primarily from our electrochemistry group. Things around blend ratios, if it's to be mixed with natural gas in the grid, assessment of odorization for leak detection, which has been since a project that we've worked on with industry following this report series. Measurement of combustion properties, looking at the suitability of the existing gas infrastructure and then materials, and this links quite heavily to corrosion, and we have a lot of capability at MPL related to corrosion and measuring and monitoring corrosion, and validated techniques for hydrogen storage, which links again to the similar capability we have in terms of CCUS, in terms of monitoring and measuring the storage mechanisms to ensure for metering, for leak detection, and to ensure that they're safe and the storage is suitable. And you can see some of the organisations for that process back in 2016. So that's everything from me. Hopefully I haven't gone over time. Apologies if I have. If anyone has any questions to follow up or any technical specific questions about any of those measurement challenges, I'm happy to put people in touch with the scientists directly. Hopefully I can answer any general questions, but thank you. That's everything from me.